All right, let's start with an overview of a variational autoencoder so that you get an idea where we are going with this lecture. And we will do that by connecting it to a familiar idea, the regular autoencoder that we already talked about last week. So here is a recap, a regular autoencoder that I showed you last week. That is what we worked with last week, where we had a neural network model consisting of two parts, an encoder and a decoder. So the encoder receives the input images X, and then it will encode these input images in a latent representation, let's call that Z. And then the decoder will reconstruct these images going back to X, so let's call this X prime, because it will not be identical to X. But our goal is to make X and X prime as similar as possible. And one way is, for instance, using the squared error or mean squared error. So here I'm writing this as the L2 difference. So the difference between X, the input, and here how I've written this, it's encoding X and then decoding X. So this whole thing here resembles X prime. So I'm minimizing the squared difference between those two. Both are vectors, so you can reshape these images as vectors, or you can just leave them as images and do the pairwise difference, and then sum up the squared differences. And if you have multiple examples, so in your batch, then you can also compute the mean squared error, where the 1 over n is over the number of examples in your mini batch. So this is what we have discussed last week. Now let's focus on the variational autoencoder, which is the topic of this lecture. So the variational autoencoder is a little bit more complicated. There is a loss node consisting of two terms. We have this term here, which is still the reconstruction loss. So overall, this is the elbow objective. So if you're familiar with that, the empirical lower bound, which consists of, let's say, a reconstruction loss here and the KL divergence. You have probably heard about the KL divergence, the Kullback-Leibler divergence in other classes before. It's essentially measuring the difference between two distributions here. And here we are assuming that this here is from a standard multivariate Gaussian distribution, so it has zero mean and the variance is 1. So this is for a univariate Gaussian, but it's of course for arbitrary dimensional Gaussians. So you can also think of this as the covariance matrix here, which is an identity matrix because we don't have any interactions between the terms. Anyways, that's a lot of jargon here. I think we will probably unpack this one by one in the upcoming videos. I think that's a lot of information here. And for this term, usually, so there are two things we can do. We can either use a binary cross entropy if we assume that the data is like a multivariate Bernoulli, or we can use the mean squared error. So the mean squared error that we also used for the regular autoencoder. And if we have something like image data where we normalize, let's say, the image data to be in the range between 0 and 1, might look like Bernoulli or something like 0 and 1, right? If you see a 0 and 1, it might look like something like a Bernoulli. But remember, here we have a range between 0 and 1. It's not 0 and 1, it's 0 and 1 and the values between. So in this way, actually using a mean squared error term for the reconstruction, like we did in the regular autoencoder, is way better than using something like cross entropy here. Although it also works to use a cross entropy, but usually in practice you would find that the images are a little bit blurrier because it will kind of be biased towards 0.5, the pixel value 0.5. But I think I will probably discuss this in a future video. So here I just gave you a lot of information. We will revisit this information in the upcoming videos. So here again, the big picture is that we have two terms. One is the KL divergence, measuring the difference between this data distribution in the latent space and the standard normal distribution. So the goal is to make this such that it looks like a standard normal distribution. And the other term is still the reconstruction loss. So we still want to create realistic looking images or reconstruct the input images. So 2 objectives now. Okay, so in the next video I will then talk about how we sample from a variational autoencoder and why, let's say, why it's interesting to use a variational autoencoder for sampling compared to the regular autoencoder. So what the advantage is essentially of a variational autoencoder.